start. Uh, my initial idea and the one that I'm following is actually doing like a zero knowledge single sign-on. So just to give some background, the single sign-on is kind of the identity provider that we use on a daily basis when we say logging with GitHub, Gmail, or some organizations use like external providers like Okta, Firebase. So these things store our identities, and we normally use usernames and password. We authenticate. There are protocols like SAML, OpenID Connect, or 2. And what I try to create is kind of like maybe this protocol of authentication authorization, but it leverages privacy. So when I have a token, I can pass my token with along with claims, but there is no way to know anything about my identity or what my claims are. It's only possible to know if I'm allowed or not allowed to perform a specific action. The additional thing that I think is kind of cool here is that you maintain your user base offline, so it's not being compromised. Because what I did is maybe just store the Merkle root hashes to do like proof of membership checks for both like roles and scope and users. And because of that, I'm also able to generate like whichever tokens I want and maybe federate access. Let's say I have like a lot of permissions and I just want to maybe delegate some action to a specific member user. I can create a token with limited scopes for the users without actually having to provisioning them. And the authentication process is non-interactive. Just the authorization. The authorization is interactive with the network in terms of you get the network state, but you don't commit any transaction. So this is what I'm trying to conceptually prove. And this is the initial design I started off. So not going to go through any of it, but it contains maybe 3 players. So it's the one that maintains the user base. It contains scopes, roles, users, and the database is maintained off-chain. A user which authenticates and has a token, passes the token to a verifier that authorizes an action that the user wants to do with the user's token. I'm moving a little fast, so if there are questions, feel free. I don't have a lot of slides. I was hoping to go through the code and how it works. So the current challenges that I'm facing when running my program is that it's computationally intensive. This is a screenshot of my processor and cores when I'm running the program. So it's not as fast as standard conservative authentication process. But there are still use cases where I think it's relevant. And the other thing is that when we do provisioning here, we need to override snapshot like the Merkle root hash. So basically, we don't have a way of incrementally like update the hash and still maintain some kind of history. At least not something that I've thought about yet. This is basically how the flow looks like. So as I said, I have 2 parts to the program. The first part is the smart contract. The smart contract is pretty simple. It holds 2 state fields, one for the maybe 3 state fields, but 2 are like most important. One for the user Merkle tree and the other for the roles Merkle tree. And it has an authorize method which validates that the token is valid and that the user is allowed to do whatever they're trying to do. And I have a zk program that the user is running and proving locally. It generates this proof that can then be sent to the smart contract. Uh, this proof contains the proof of membership for the user and that the role that the user is hashed with is actually an actual role with actual scopes and is part of the tree. So this program also gets the network states, verifies everything, and then like the token is valid and can be used against the smart contract. Okay, great. So I'd like to dive into the code, show you the parts if you want. Maybe starts with the basic building blocks here. Uh, so I have this library and contains like a scope. Scope is like maybe the most atomic uh, building block. It's actually just a value, and the name is not being hashed, right? It's just a string. But the value is some kind of a number. Then the role contains a list of scopes. I've limited to 10, but you can just if you can modify the contract to match your specific requirements. I think 10 is sufficient for the demo. And then what the contract, what the role does is when it gets hashed, so it hashes the scopes together. And then we have the user. The user is basically a public key and the role. And currently, I only like the only way to initialize it is with a private key because passing the public key is pretty easy to like fake a user and a token. So I wanted to do that. For the future, I also plan on integrating with Oro wallet extension when I invest more in the UI. And so these are the building blocks. We have the smart contract, which is fairly simple. So it stores the user store commitment, the role store committed, and max token lifetime, which can be taken from the smart contract, so that we know that when a token is issued, it has an expiration, and that the user cannot set, for example, for it to expire in a year, it's limited to this amount of seconds, right? And then we have like this method to update the contract, which should be called whenever I maintain my user base or I add roles. And then this is the authorize. But before we go on to the authorize, let's chronologically look at the flow. So we have this token zk program, and it accepts like public information and private information. And it generates an authentication proof. So in terms of like the public things that it gets like a list of scope. And what it does is the scopes are hashed, right, with the issue time of the token, so that it's going to be a little harder to correlate like which scopes a user holds, like by comparing tokens. For example, so if I have like a specific list of scopes, I can compare it and see, oh, this user which with this token also has these scopes. So it adds a little like some privacy to it. And then the issue date, expiration, and the commitments from the network, right? Okay. Sorry, not the commitments from the network, but oh yeah, those are the commitments from the network. And then we have the private arguments, which obviously the private key, the role. So this is the actual role object. It should be publicly available or with some limited scope available to users who want to log in. And then this is the only way to generate the user in relation to the token. And what we're doing with the init method for the token is basically just checking that the user, like with its Merkle path, is actually part of the user store, and that the role that he uses is part of the role store. And yeah, and once we do that, we know that the user is authenticated, like that the user is who they say they are, right? Uh, any questions so far? Because I don't really see you. I see the screen, so I don't know. Like, okay, now I see. Okay, so once the user is authenticated, now they want to use the token, and so the they want to send like a scope and see if they're authorized to use this scope. So yeah, the first thing we do is we take the zkApp program, we verify the proof, and we compare the commitments from the zkApp, like from the token to the ones on the network. So let's say I created a token, but I used my own Miracle tree with my own scopes. So this should fail. And then for the network time, I compare it with the issuing time and expiration time, and see that um, that the user did not tamper with the with the token, or set like a very long expiration date, or did anything malicious with it. Uh, and then we also check that the expiration time is not larger than the sorry, it's larger than the issue time. The issue time is not larger than the expiration time. And last, and this is a bug, by the way, that I found but didn't have enough time to fix, is I checked that the scope that I hashed with the issuing time is actually part of the scopes on the zk program. And the bug is that indeed I'm checking it, but I don't give any feedback about it. So I'm authorizing all token users, and what I need to do is maybe compare it, like asserting that it's a Boolean true, right? And okay, so in terms of what we saw here, the logging in and authorizing, I've created some helper methods for the demo. I ran it like, okay, maybe let's start with the database. So I used the OpenAPI example for a pet store, right? And took those codes and created like, let's see. Yeah, okay. I created a list of scopes, roles, and users. The users are represented by public key, and the role. So I created 4 users, each one with a different role, and each role has different scopes. So admin has all the scopes, pet manager can read pets, write pets, and read inventory. A sales rep can read inventory, read orders, and write orders. And a store manager has like almost all the scopes except for user read and user write, right? And what I did is when setting this up, just created the Merkle trees and committed the hashes to the network. So once this is done, just created like a public info listing. So this is what's going to be publicly available. Not a lot of personal information or anything that can, let us know what we have. We do have the like the roles and scopes that we need, and I didn't find a proper way to obfuscate them, but I think I can have a breakthrough here. And so this is information that's required in order to do the authentication authority, basically the token creation. Let's see. So what we have here is we have the keys, like the private keys for those users for the demo, and we have the hashes for the roles, and then we just like create a users, and these are actually helper methods. So when we try to log in, um, we get the timestamp from the network, and we get the scopes from the public info, and then when we do get out state, so we add the time to the expiration, we get the scopes, and we init. This is the public information, right? And we then create the private information with the private key, the time, and the role that we're creating that's comprised of string and the scopes. It's just a collection of scopes. And we get the Merkle path for it and the user Merkle path, which we get before login, and then we create a token. And this is the part that really takes a long time. And then for authorization, so what we log in, we write the token to a file. So maybe we can pass it. Just going to show you how the token looks like. Let's
Also,
see.
just a quick
Yeah.
quick jump in. Is it okay just one more minute to show this? We need to move on. But
Yeah, sorry. So just for we keep the token, and then for authorization, what we do is we call the authorize method that I showed on the smart contract, and then we get like either we prove it or it raises an exception that we catch and says that it's unauthorized. This is basically it. If you have any questions, I guess this is the time.